normal ant with doing their conversions and figuring out all kinds of ways, the formula, that their consumption of air would be, or oxygen would be 0.55 milliliters per centimeters squared. Now, if you double the ant size to see if it would work as a double ant, you would double the radius and double the height, which would then make the consumption of oxygen 22.17 milliliters per centimeter squared.
Now, I have a question. Why does that number, the first number, the 0.55, and it changes to
22. So even though the ant is doubled in size, it needs 4 times as much oxygen to survive.
Did anybody make those ants and see the difference in the actual amount of paper that you use? And why isn't it just double?
Because it doubles on both dimensions.
Doubles both dimensions, right? The height and the circumference. Okay. And then where did you get, I see at the top there's a 0.89. Where's that from?
This right here, the 0.89?
Yeah, where'd that come from?
That would be if you took this and you could use the converted numbers, because the normal 8 centimeters, if you use 8 centimeters and 1.5 centimeters for the radius and height, you get 89. But you need to convert that, so it would be 80.89 centimeters squared.
And does anybody have a question about why did you go from 89?
Google.
Yeah.
We have a formula for the surface area of the cylinder.
Okay.
And it was 2 pi r squared plus 2 pi r times height.
2 pi r times height.
H.
All right, so let's talk about this. What does all this mean? What is this?
The area.
Okay, those are the 2 bases, right? When I make my cylinder, I have 2 circles.
Did anybody get those circles in their model?
And so the area of these little circles are going to be pi r squared, right? But I got 2 of them. Okay, so that's what this is. What's all this stuff? Who wants to talk us through what this is? Where do those numbers come from? Tell us where that comes from.
Well, we didn't exactly do it that way. We had the 2 circles on the end.
Okay.
And then we realized that in order to find the wall of the cylinder, that is going to be the given height of the cylinder, which was given to us in the directions. But then in order for us to know how many, what the x value is going to be, the width, that would be identical to the diameter. And so we used the formula that we already knew, that that pi is the circumference divided by the diameter, and so the circumference would be pi times the diameter. And then we got that value, and then we added it to the other 2 values to get the total.
Pi times, and then I just got the diameter. And we knew what the diameter was, right? We knew it was 3. So then it's, 3. If we're in Texas, pi apparently is 3. I don't know if you know that. I think they decided it was pi. I mean, it was 3. But that's your dimension here and here, or if we count the squares, right? It's approximately an 8 by 9 or 8 by 9.5 rectangle. And what did you call it? You called it the
area of the cylinder.
The wall. I was trying to think of what do you call that part? The wall of the cylinder, right? So there's the wall of the cylinder. So whoever asked the question about where the numbers came from, did that work for you? Okay, thank you. Thank you for asking. Okay. So we determined that if there's really an ant that's really this big, it's not going to survive. If it's the actual 8 millimeter ant, I think we've determined you can play with it some more because that is the size of a typical ant. But the question would be, how big can an ant get given what the constraints are that we have? Okay? And Tachi was going to share with us just briefly, there are some other theories about why you don't have giant ants. You want to talk a little bit about, just quickly about that, because I know we're moving on. Because they're roving.
So I think I mentioned a couple of the hypotheses already. Another one that is mentioned in the literature is whether their legs can hold their weight. So there are limitations as to how big they can get because as you scale, as you realize with your model, as you scale something up, dimensions change, and the mass of the body of the insect would just crush its appendages. So that's one fun thing that you can try to calculate too, and an activity that you can try to do that's maybe a little less complex than the air. But I think in the end, it still has to do with the air because the legs can't grow too much because there's not enough oxygen getting through the tracheal system in the legs to provide energy for the legs to grow muscle and tissue enough to hold the insect up. One of our colleagues, Larry Horvath, he did some research at UC Davis, and one of their research projects was to feed cockroach and provide it with air in a very nice environment and see how much it grew. And he said that cockroach got about this big. But it fell, it crushed its own appendages, and they had to kind of keep it up with some sticks, and it was pretty sad. But yeah, so there are various ways in which you can utilize this information to calculate.
So the last thing I want to leave you with before we move on is thinking about, again, how the dimensions, how they change, how the square dimensions and the cubic dimensions change when you double the linear dimensions. Right? So if you did the volume of a certain size and then double the dimensions, was the volume of the next bigger size double? Right, it was more, a lot more than double. Much, in the same way that when we just doubled the dimensions of this guy, the surface area was not doubled.
People were doing in the ant activity, we realized that scaling is hard. We already knew scaling was hard, but it was just a reminder to be going around. All of us are pretty smart, and all of us get pretty confused scaling. And so we were thinking, man, what we really should have done is start off with an activity that really narrowed in on the issue of scaling. And sort of a very simplified version of it, so we could focus on the scaling part of it. And what happens to the dimensions as you scale? And then we thought, it's not too late. They're still in the room. So Allie's going to have us do some stuff with that.
So yeah, just to kind of build off of what Eric just said, one of the things that we have to do in this grant is figure out who everyone in the room is and what you need and what's going to be helpful for you as you go into your classrooms, what you can take. And so I'm sitting over here with a table of third grade teachers, and they're like, I would never do this with my third graders. So what can I do? And so this is kind of a modified look at the ant activity, where we use things that could be appropriate for third grade, but also could be extended well into 8th grade. So this is something that we can all kind of reframe our thinking. So rather than a cylindrical ant, I want to introduce you to my friend, the bot. I'm calling him a bot, a B-O-T-T, a bot. So my bot is 2 linker cubes stuck together. And now even a very young student can look at my bot and can take down some of its vital data. Can you, in your groups, figure out what is the volume of my bot and what is the surface area of my bot? Take just a couple minutes, build a bot, calculate its volume, calculate its surface area. Just one bot. Alrighty, 1, 2, 3, eyes up here. D-bot. Now, we should be able to take our D-bot and count up how many of those linker cubes it took to build it. So how many linker cubes did it take to build a D-bot? 16. All right, so I'm going to take that number, I'm going to write it down. And how many squares make its surface? 40?
Hallie, do you want to put it on the chart?
I'm done. Okay. So now what I've done is I've taken my data and put it into a table. And now the question that I want to start asking is, what's going on here with the growth between my bot and my D-bot with the surface area and with the volume? So what we'll eventually do here in the next couple of days is to take the ants activity, scale it, so that it would be appropriate for a third, fourth, and fifth grade classroom with the linker cubes. We'll put that up on the website for you. Thank you. All right.
Thanks, Alex. Okay, so for the last segment of this day, yeah, if you could, that's all we're going to do with the cubes for now. But tomorrow,